Every year, electrical cables are undersized on industrial projects across the world. Not because engineers don't know Ohm's law, but because cable sizing is not one calculation. It is 4 simultaneous criteria, and most calculations stop after the first one. In this video, you are going to learn the complete framework: current carrying capacity, derating factors, voltage drop, short circuit withstand, and protection coordination. The same methodology used by consulting engineers on industrial, mining, and infrastructure projects. Let's start from the beginning. Cable sizing is the process of selecting the correct conductor cross-sectional area, measured in square millimeters, and the right cable construction for a specific electrical circuit. The cross-sectional area directly controls 2 things: the resistance of the conductor, and therefore how much heat it generates, and the physical current it can carry without exceeding its insulation temperature limit. But selecting a cable is not simply picking a number from a manufacturer table. Every cable selection must satisfy 4 independent engineering criteria. First, the cable must carry the design current without overheating. Second, it must maintain acceptable voltage at the load terminals. Third, it must survive a fault current long enough for the protection device to clear that fault. And fourth, the protection device— An undersized cable running above its thermal limit degrades its insulation with every hour of operation. The relationship is not linear. Running a cable just 10 degrees above its rated temperature can reduce its service life by 50%. Eventually, insulation fails, producing arcing, fault current, and fire risk. The second failure mode is voltage drop. When a cable has insufficient cross-sectional area, its resistance causes a significant voltage drop along its length. For a motor circuit, this can mean the terminal voltage during starting falls below 85% of nominal. The motor cannot develop sufficient torque, it stalls, draws locked rotor current, and overheats. Third, short circuit failure. During a fault, the cable must absorb enormous thermal energy for the time it takes the protection device to clear the fault. If the cable is undersized for this duty, it is destroyed before the circuit is interrupted. And fourth, from the project cost side, oversizing cables— Before selecting any cable, you need the design current, the current the cable will actually carry under maximum operating conditions. For a 3-phase motor, the full load current is calculated as follows: I equals P divided by the product of √3 times line voltage times motor efficiency times power factor. Let's break down each term. P is the motor's rated shaft power in watts. √3, 1.732, accounts for 3-phase power distribution. V is the line-to-line supply voltage. Eta is the motor efficiency, typically 0.88 to 0.95 for modern machines. And cosine phi is the operating power factor, typically 0.80 to 0.90 for induction motors at full load. Combining these, a 75 kilowatt motor on a 400 volt supply with efficiency 0.92 and power factor 0.85 draws a full load current of approximately 138 amperes. This becomes the design current, IB, which is the starting point for every subsequent calculation. For feeder circuits, every conductor carrying current generates heat in proportion to current squared multiplied by resistance. This is Joule heating. That heat must conduct away to the surrounding environment. The cable's rated current, called IS in the standards, is the maximum current that the cable can carry continuously in a defined set of reference conditions without exceeding its insulation temperature limit. For XLPE insulated cables, that limit is 90 degrees Celsius. For PVC, it is 70 degrees. The keyword is reference conditions. Standards such as IEC 60364 and AS/NZS 3008 publish current ratings assuming an ambient air temperature of 30 degrees, a single isolated circuit, no neighboring cables, and standard soil conditions for buried cables. Change any of these conditions, and the tabulated rating no longer applies directly. It must be corrected. The installation method has one of the largest effects on current rating. A cable clipped to a wall in free air dissipates heat efficiently. Derating factors are correction multipliers applied to the tabulated current rating to account for actual site conditions. There are three primary factors engineers must evaluate. The first is CA, the ambient temperature correction factor. If the ambient temperature is higher than the standard reference of 30 degrees Celsius, the cable can dissipate less heat, so its effective rating must be reduced. The formula is CA equals the square root of the insulation's maximum temperature minus the actual ambient temperature, divided by the insulation's maximum temperature minus the reference temperature. For an XLPE cable at 45 degrees ambient, CA is 0.87, meaning the cable's effective rating is 87% of its tabulated value. The second factor is CG, the grouping correction. When multiple cables are installed on the same tray or in the same conduit, they cannot dissipate heat as freely because neighboring cables are also generating heat. 3 cables together, CG is 0.70. 6 cables, 0.57. 12 cables, 0.45. The third factor, CS, applies to buried cables and corrects for soil thermal resistivity. In arid conditions with dry, sandy soil, voltage drop is the reduction in voltage between the supply point and the load terminals, caused by current flowing through the cable's resistance and reactance. For 3-phase circuits, the line-to-line voltage drop equals √3 multiplied by the design current, multiplied by cable length in kilometers, multiplied by the quantity, resistance per kilometer times cosine phi, plus reactance per kilometer times sine phi. Resistance is the dominant term for smaller cables. Reactance becomes significant for larger cross-sections above 70 square millimeters. 2 important corrections engineers often miss. First, conductor resistance increases with temperature. A cable operating at 75 degrees Celsius has approximately 20% higher resistance than at 20 degrees. Using the cold resistance underestimates voltage drop. Second, check voltage drop at both full load and motor starting. Starting current of 6 to 8 times full load through the same cable impedance produces a voltage drop. During a short circuit fault, current of many thousands of amperes flows through the cable for the time it takes the protection device to interrupt the circuit. That current generates intense heat in the conductor. The cable must absorb all that energy without the conductor temperature exceeding the maximum value the insulation can tolerate during the adiabatic, that is, no heat loss, period of the fault. The minimum cable cross-sectional area for short circuit withstand is calculated using the adiabatic equation. A minimum equals the prospective short circuit current, multiplied by the square root of fault clearance time, all divided by the K factor. The K factor encapsulates the conductor material, insulation type, and initial temperature. For copper conductors with XLPE insulation, K is 143. For copper with PVC, K is 115. For aluminium with XLPE, K is 94. As an example, a 10 kiloamp fault cleared in 0.1 seconds on a copper XLPE cable requires a minimum conductor area. Protection coordination ensures the protection device, cable, and load operate as a safe system. The fundamental rule from IEC 60364 states, the design current must be less than or equal to the protection device rating, which must be less than or equal to the cable's current carrying capacity. IB less than or equal to IN less than or equal to IS. A protection device rated above the cable's ampacity defeats the thermal protection the cable needs. The cable can overheat before the device trips. For motor circuits, protection is typically layered. The thermal overload relay, set at 100 to 105% of full load current, protects against sustained overload. The molded case circuit breaker provides short circuit interruption capability. The contactor switches the motor. Now let's apply everything in one complete worked example. The scenario: a 75 kilowatt, 400 volt, 3-phase induction motor. Cable route: 30 meters. Installation method: multi-core cable clipped direct to cable tray with 4 circuits total. Ambient temperature: 40 degrees Celsius. XLPE insulated copper cable. Supply fault level: 10 kiloamperes. Protection device: molded case circuit breaker, 0.1 second clearing time. Step 1: full load current, 75,000 divided by root 3 times 400 times 0.92 times 0.85. This gives us 138 amperes. This is our design current EB. Step 2: derating. Ambient 40 degrees, XLPE, CA is 0.91, 4 circuits on tray, touching, CG is 0.65. Combined derating, 0.91 times 0.65 equals 0.592. Required tabulated rating, 138 divided by 1.592 equals 233 amperes minimum. Step 3: cable selection, 70 square millimeter is rated 220 amperes, not sufficient. 95 square millimeter is rated 265 amperes. After derating, 265 times 0.592 equals 157 amperes. This exceeds 138 amperes. Criterion: 1 passes. Step 4: voltage drop. Resistance: 0.247 ohms per kilometer at operating temperature. Reactance: 0.080 ohms per kilometer. VD equals root 3 times 138 times 0.030 times open bracket, 0.247 times 0.85 plus 0.080 times 0.527 close bracket. Result: 1.60 volts, 0.40%, well within the 5% limit. Criterion: 2 passes. Step 5: short circuit withstand. Amin equals 10,000 times root 0.1 divided by 143 equals 22 square millimeters. 95 square millimeter far exceeds this. Criterion: 3 passes. Step 6: protection device, 150 ampere MCCB, IB 138 in 150 is effective 157, all compliant. 140 ampere thermal overload relay. Final result: 95 square millimeter copper XLPE multi-core cable. 150 ampere MCCB, 140 ampere thermal overload relay. All 4 criteria satisfied. Before we move to the professional workflow, let's lock in the 5 most common mistakes in cable sizing practice. Mistake 1: ignoring grouping factors. Every cable on a shared tray must have grouping applied. The standard does not provide an exemption for lightly loaded cables. Mistake 2: using the wrong installation method rating. Always confirm how the cable is actually installed before selecting a current rating table. Mistake 3: skipping the starting voltage drop check on motor circuits. Full load voltage drop compliance does not guarantee starting compliance. Mistake 4: treating short circuit withstand as optional. It is a mandatory criterion under every major cable sizing standard. Mistake 5: selecting a protection device independently. Here is the professional cable sizing workflow you can apply immediately to any project. Step 1: confirm your load current, IB. Step 2: identify your installation method. Step 3: select a candidate cable from the relevant current rating table. Step 4: apply all derating factors simultaneously and verify effective is exceeds IB. Step 5: calculate percentage voltage drop. Iterate with a larger cable if the limit is exceeded. Step 6: verify short circuit withstand using the adiabatic equation. Step 7: select and coordinate. If this video gave you a clearer framework for cable sizing, subscribe and check the description for the free cable sizing checklist. I'll see you in the next one.